Consider a NACA 2412 airfoil with a chord of 0.64 meters and an airstream at standard sea level conditions. Now the free stream velocity is 70 meters per second and the lift per unit span is 1,254 newtons per meter. Now what we want to do is calculate the angle of attack and the drag per unit span. So now at sea level, density of the air is going to be equal to 1.225 kilogram per meter cubed. And now this is important because our first step is calculating the dynamic pressure, denoted by Q infinity, which is equal to 1/2 rho infinity V infinity squared. So we're given rho is 1.225 kilogram per meter cubed, and V infinity as 70 meters per second squared. So then the dynamic pressure will be equal to 3,013.5 pascals. So now the next step is to solve for the lift coefficient. So we can say that CL is equal to L, or lift, divided by dynamic pressure times the surface area of the wing. But in this case, we have the lift per unit span instead of the lift. So what we'll have to do is we can denote the lift per unit span as L prime, and we'll divide by Q infinity, or the dynamic pressure, as the same. But then for the surface area of the plane, we'll actually break that up into the chord length times 1. So then the units will line up. So we'll have C times 1, replacing our surface area here. So now we have our coefficient of lift in terms of our lift per unit span. And then next, all we have to do is plug in our values. So then that gives a coefficient of lift equal to 0.65. So now what we need to figure out is with CL equal to 0.65, what is alpha equal to? So what we can actually do is we can use these two tables off to the side, more specifically this first one up top. So we said we had a lift coefficient of about 0.65. So essentially draw that line across till we hit our lift curve slope, and then we'll just drop our line directly down. So it looks like alpha is about 4 degrees. And then that is the first answer to the problem. Now, before we start trying to calculate the drag per unit span, at sea level, we need viscosity. So that's why we have to define our viscosity, mu, is equal to 1.789 times 10 to the negative 5 kilogram per meter second. And it only equals that at sea level. So that's very important to consider. So now, what we can then do is solve for the Reynolds number, which is equal to rho infinity times V infinity times the chord length divided by, wait for it, mu infinity. And since we're all at sea level, we're going to use our sea level values. So we can start plugging stuff in. So for rho, we got 1.225 kilogram per meter cubed. For V infinity, we got 70 meters per second. Chord length is 0.64 meters. And then viscosity is going to be same as before. So this leaves a Reynolds number equal to 3.08 times 10 to the 6. And the Reynolds number is always unitless. So now we can say with alpha equal to 4 degrees and Reynolds number equal to 3.08 times 10 to the 6, we need to solve for our coefficient of drag. Now that's where this second table or second graph comes in handy. So what we can do is we can first look at the Reynolds number, because we have two different ones here that they give us. We have 3.1 times 10 to the 6 and then 8.9 times 10 to the 6, because this will affect what drag coefficient we'll get. So since ours is 3.08, we'll go more with this circle one here. So let's take our red line here, and we'll start at a alpha, or angle of attack, of 4, and we'll go up to the circle lines approximately. And then we'll essentially just draw a line over to get our CD, which that looks like it's about 0.0068. 0068. Okay, so now that we have all of our values, we can solve for the drag per unit span. So that's going to be equal to Q infinity times our coefficient of drag times our chord length. Because remember, we have to split up S. So drag is going to be Q infinity times S times CD. But in this case, we're solving for our drag per unit span. So then we essentially have to break up S into C and then times 1. So that's why we are doing that. So it's pretty much the same as before. And then we can just start plugging in values. So we have 3013.5 pascals for dynamic pressure. And then we have 0.0068 for the coefficient of drag. And then 0.64 meters for the chord length. That leaves a drag per unit span of 13.1 Newton per meter.